Here it is, the periodic table. So all of you guys should be a little bit familiar with this from middle school, but this is how the basic elements are organized. If you need a review of what an element is, let's say you take something like a piece of bread, and you keep slicing it in half, and slicing it in half, and slicing it in half, and slicing it in half. Well, every slice is a piece of bread. Well, eventually you keep slicing, you're going to get a piece so tiny that when you cut it apart, there's going to be two different parts. The parts will not be the same as each other, and those are elements. So here they are, they're organized. Remember, these were all discovered at different times, and somebody, Mendeleev, was very smart and figured out how to organize these. Okay, the first thing I want you to notice is that the elements usually have symbols that represent the element. They are typically one letter. For example, hydrogen here has one letter, but they often have two letters as well. Okay, so that would be lithium there. Sometimes, on occasion, the symbol here, Na, really is not the first two letters of sodium, which would be So. So there are names that go back far in time that are sometimes different than the names we use today, and so you just have to be aware of that. Also, you will notice that always, 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 the letter is capitalized, and if there's two letters, the first is capitalized and the second is lowercase. Okay, if you remember, these are organized based on certain characteristics they have. For example, it could be the melting point, could be based on their boiling, could be based on their densities. All these properties kind of seem to line up in some organized way that produces the periodic table. So all of these elements right here share many characteristics. Remember, those characteristics are called physical and chemical properties. The periodic table is primarily organized based on its chemical properties, the way it goes through chemical changes. Okay, so if certain characteristics or chemical properties are the way in which the periodic table is organized, then it matters how close different elements are to each other. So, for example, here calcium and potassium are somewhat similar because they're close to each other on the periodic table. But because magnesium and calcium are in the same group, their similarities are much more than calcium with potassium. So up here we have groups. Remember, these are groups. They're also called families. And they are the most important way that elements are organized on the periodic table. Okay, one of the things you should notice right away with the periodic table is that the way it's organized. So we start with 1 here, right? And we go over to 2 here, and then we swing back around to the other side. We got 3, 4, 5, 6, 7, 8, 9, 10, and then swings around to 11, and it just keeps going on and on like this. These are the atomic numbers, and these are the way that the periodic table is organized. And let's talk for a minute what an atomic number is and also what the atomic mass is. Okay, first let's talk about atomic mass. So, what is atomic mass? Well, there were some clever chemists back in the day who realized that when you combine certain elements, they all seemed to be in a certain ratio to each other. So, for example, when you combine certain elements together, for example, calcium, magnesium, oxygen, and hydrogen, that there seem to be almost perfect ratios. So 1 gram of hydrogen, 16 grams of oxygen, not perfect, but about 24 grams of magnesium and about 40 grams of calcium all seem to combine together in a particular ratio so that there was none of the elements left over at the end. So Dalton came up with this theory that if hydrogen is 1, that all the other elements will be some ratio of hydrogen. So this is 16 times the hydrogen, this is about 24 times the hydrogen, this is about 40 times the hydrogen. And that if hydrogen is 1, all the other elements will be some ratio of that other hydrogen. Okay, well, Dalton's theory had a little bit of problems because hydrogen had some issues. We had some things that didn't line up very well with hydrogen. So what they ended up doing was they ended up using carbon. So if carbon is 12, you would divide by 12, and that's going to give you 1. So carbon became the standard, so that 1/12 of carbon became 1 atomic mass unit, ATM. And all the elements are based on how many atomic mass units they have, and that's where atomic mass came from. Okay, if we look at the nucleus of an atom, we know that there are protons and neutrons in the nucleus, and that they are most of the mass of the atom. There's very little mass contained in electrons. It's so tiny that it's insignificant, we don't even really count it. If we look at this drawing, we can see that there are red and blue particles. The red particles are going to be protons, and the white particles are neutrons. If we look at this nucleus right here, the 6 is going to represent the number of protons in that nucleus. The 12, that's going to represent the total number of particles in this atom. So if we look, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 particles in the nucleus. But only 6 of them are protons. So 12 minus 6 equals 6. That means there's also 6 neutrons. Okay, if we look at this nucleus over here, it's a little different. You can tell there's a lot more of the white particles, which means that the number of protons has stayed the same, but the number of neutrons has changed. If we count them up, there would be 14 total particles, but only 6 of them are protons. The number of protons defines the atomic number. So since both of these particles have the same number of protons, 6 and 6, that means that they are the same element. Carbon will always have 6 protons, but they're different. Because they're different, they have a name. The name of an element that has the same number of protons but has different number of neutrons is called an isotope. So while these are both carbon, they are different types of carbon. This one is carbon 12 and this one is carbon 14. These are 2 different isotopes of the same element. So obviously the number of neutrons must be different. I also want you to realize that the element is defined by the number of protons that it has, which is also the same thing as the atomic number. Okay, so these atomic numbers here on the bottom, those are the number of protons, and every carbon atom has 6 protons. Every single oxygen atom has 7 protons. So doesn't matter what the isotopes are, the number of protons will always be the same for that element. When the neutrons change, that means it's a different isotope. Okay, so on this periodic table you can identify where the atomic numbers are. They're at the top of the boxes. We have the different ones for the different elements. And then at the bottom we have the atomic masses for the different elements. And so you might look at some of these atomic masses and think, wait a second, what's going on? This says 83.80. How could it be that there are 0.8 neutrons? Does that mean that the protons and neutrons can be in pieces? No, it doesn't. What this means is that this is an average of the different isotopes that krypton can have. So many of the isotopes are 83 particles in their nucleus, but many of them also have 84 particles in their nucleus. So if this was an average, and let's say there were only the 2 isotopes, 83 and 84, that means that if we had 100 atoms of krypton, 80 of them would be 83 particles in the nucleus, and then 20 of them would be 84 particles in the nucleus. This would be an average of the 83 and the 84 for all the atoms. Okay, for one clever student, we can talk about this in class. Why are there some of these elements that have parentheses and they have a whole number for their atomic mass? You see a few of them here. There's one here. There's one here. Think about this and let me know if you figured out why they have parentheses and why they're whole numbers. Okay, so a quick refresher. Elements are organized on the periodic table into groups or families. This is based on certain physical and chemical properties they have. We have atomic numbers, which represent the number of protons in an atom. Protons are positive, neutrons have no charge, and electrons are negatively charged. We sort them based on their chemical properties, and they are organized based on their atomic number, not on their atomic mass. So I bet somewhere on here we could find one that was actually went down in its atomic mass. Let's see if I can find one here. Okay, so let's look at this right here. We have technetium and iodine. So the atomic mass goes from 127.6 down to 26.9. So that proves that the periodic table is organized based on atomic number, not on atomic mass. So here's the periodic table in a nutshell, how it's organized, and talk to you soon.